Hello everybody. Welcome to our lecture on logical deduction in artificial intelligence. In earlier lectures in the direct class, we have done propositional or Boolean logic, and we have studied how we model problems using Boolean or propositional logic and how we analyze them and carry out deduction or inference. Today, we shall move on to what is first order logic, or also known as predicate logic. If you recall the steps that we had done in propositional or Boolean logic, they consisted of basically 5 steps. The first step was the choice of Boolean variables. We would identify a set of Boolean variables A, B, C, D, etc., which could take either true value or false value. Then we would use the whole of Boolean logic. Boolean logic is defined by a set of syntax and semantics. The syntax consists of connectors, OR connector, which is the OR connector, the AND connector, which is the AND, and then we have the implication connector, which is the same. A implies B is the same as not A or B. We also had the negate connector, which can be written this way or sometimes this way. And then there are other derived connectors, the XOR connector and several other connectors. The semantics or the meaning of these are defined by truth tables, and we are all aware of the truth tables, and we know that and, or, and not, or maybe just or and not, or and not, are sufficient enough to give the complete expression. The third step in our methodology was called codification of sentences, which means that given English language sentences, we would codify those sentences into standard Boolean formulae using the Boolean variables that we have chosen. After we had codified that whole process, then the whole deduction process would be converted to a single formula. And once this combined formula would be generated, and this combined formula would be then used for our deduction process. In our deduction process, in order to prove the truth of that formula, we would check what is called the validity of the formula, which means that we would check whether the formula is a tautology. In some cases, we would also check what is called the satisfiability of the formula. A formula is said to be valid if it is true for every assignment of the Boolean variables, and a formula is said to be satisfiable if it is true for some assignment of the Boolean variables. And using this validity and satisfiability, we would use this idea to try and understand the level of truth of the formula. And based on that, we would go back to the English language sentences that we had codified and then try to say whether the inferencing was correct or not. Let us revise with an example. Here is an example, the first example. This is an example which we had probably done before, but just for revision and recapitulation. It says that if I am the president, then I am well known. I am the president, so I am well known. It is obvious to us who look at English, we know that this is correct. So now, how do we go about the steps? The first step is identification of the Boolean variables. So here we identify the Boolean variables as follows. I am the president is identified as one Boolean variable, and we call it A. I am well known is identified as the second Boolean variable and we call it B. So we have now two Boolean variables, A and B. A says I am the president. If A is true, then I am the president is true. If A is false, I am the president is not true. B is I am well known. B is true means I am well known. B is false means I am not well known. This is the first step of codifying and identifying the Boolean variables. The second, this step now is the sentence codification. The sentence codification, we have three sentences. First sentence is F1, which is if I am the president, then I am well known. So how do I codify that sentence? That sentence is codified by this formula that if I am the president, A implies B. That means if I am the president, then I am well known. So A implies B, which is also the same as not A or B. The second sentence is I am the president. So F2 is codified as A. And therefore, that means the thing that I want to infer is called I am well known. So my goal is I am well known. So I have now done this step, which is codification of the sentences. Now I need to find a combined formula. What does the combined formula say? That the first sentence F1 and F2 derive or infer F3. That means F1 and F2 implies G. This is what it means. Therefore, the formula for deduction is F1 and F2 implies G. And in our case, it becomes A implies B, which is F1, A, which is F2, and B, which is goal. And what do we have to prove? That this formula is true. Always true. In other words, it means that this formula is a tautology. A formula being a tautology means it is true for every assignment of A and B. So now, all we now have to do is prove that this is a tautology. There are various ways of proving this is a tautology. And one simple way of proving this is a tautology is by creating what are called truth tables. So here is a truth table. The truth table has got A, B, and all possible combinations of A and B, which means A could be true, A could be true, B could be false, A could be false, B could be true, both could be false. From this we see A implies B, which is the same, A implies B, which is equivalent to not A or B. This is equivalent to not A or B. So this, if both are true, this is true. If this is true and this is false, then this is false, because not A becomes false. If this is false and this is true, it is true. If both are false, it is true. The next part of our formula is this part. So now we have A implies B, whose truth we have here, and A whose truth we have here. And we need to do an AND of the column 1 and the column 3. Once we do an AND of the column 1 and column 3, we get the column 4. And column 5 is this part. Column 4 implies column 2. And we can see true, true. So if this is true and this is true, obviously this is true. If this is false and this is false, this is true, because A implies B is true if A is false. So if any formula P implies Q, this is the same as not P or Q. This formula will be true if P is false. This formula will be true if both P is true and Q is true. and this formula will be false only under the condition that P is true and Q is false. So here again this side all are false, so this is true. So now we see that this formula, which is our combined formula that we generated from F1 and F2 implies G, is a tautology. By this we are able to deduce that if I am the president, then I am well known. Given this, and given that I am the president, I can infer that I am well known. So this is a simple method that we had done, and we recapitulate. We look at our second example, a very similar example. If I am the president, then I am well known, which is the same as before. Now I am saying I am not the president, and I want to infer that I am not well known. So my codifications remain the same. F1 remains the same. F2 is now not A, because I am not the president. And G is now not B. So G is not B. And my formula again is the same. F1 and F2 implies G is a tautology. And we again do the same thing, but here in this case we find that this row, when A is false, which means not A is true, when B is true, in that case we see A implies B and A and not A is true. But since we have not B is something that we want to derive, and B is true here, so we will get a formula where the left hand side, which is this part, for this row, this part is true, and since B is true, this part is false. Therefore this formula is false. Therefore this formula is not a tautology. It means that this formula is not satisfied for this row. Each such row is called an interpretation. And if there is one interpretation for which the formula is false, then the formula is not a tautology. A formula which is true for all interpretations is known as a valid formula, and this formula is not valid. And it is obvious from this example, if I am the president, then I am well known. I am not the president. I cannot derive that I am not well known, because I could be not well known. I could be well known for some other reason. So as we see, these are examples of propositional logic. We have done several other detailed and much more complex examples in the earlier classes, but this was just the background for us to move on. Propositional logic, as we know, is not sufficient for modeling many other problems. Here are 4 examples that we are trying to see. The first example says, wherever Mary goes, so does the lamb. Mary goes to school, so the lamb goes to school. Now, how do we model this as Boolean? How do we model this using Boolean formulae and Boolean variables? It's easy to Mary goes to school as one Boolean variable. Lamb goes to school as another Boolean variable. But we will have enormous difficulty to model this, because here we are not saying where Mary goes. We are just saying wherever Mary goes, so does the lamb. So this sort of sentences cannot be modeled by Boolean logic, because we do not know how many formulae to give. We do not know where Mary goes, and so on and so forth. Look at the second example. No contractors are dependable, which means every contractor is not dependable. Some engineers are contractors. We are not saying which engineer is a contractor. And this would we want to deduce that some engineers are not dependable. So here, all see we are even wherever Mary goes, no one is dependable, someone is dependable. So these issues of where we are talking about all people, where we are talking about some people, where we are talking about no person, these are not easily modeled using Boolean logic or propositional logic. Similarly, the third example, all dancers are graceful, this all. Ayesha is a student. This can be modeled by a Boolean formula. Ayesha is a dancer can be modeled by a Boolean formula. But some student is graceful cannot be modeled by a Boolean formula. The last example in our case is very interesting. Here again, every passenger, which means every passenger is either in the first class or in the second class. So every is like an all passengers. Each passenger is in the second class if and only if she is not wealthy. So each passenger, here again is an all. Some passengers are wealthy. Here again is a sum. Not all passengers are. So this now talks about not everyone. Then we want to deduce that some passengers are in the second class. So if you look at all these four problems from an English language point of view, we can say that yes, we can do a deduction. But how do we model them? How do we codify them? How do we go back to the steps that we had seen before in terms of these steps? Modeling, codification, development of the combined formula, and proof of the validity or the tautology, or proof that it is always true. So in order to do that, as we had seen, we now need certain new concepts to be added. So what we start doing is, take the case of wherever. Since there is a concept of wherever, we now need to model this concept using variables. So Mary goes. Where does Mary go? So we have to model this with variables, saying it goes to some place X. Then we will see constants. And since we are using variables, we will have to use now some symbols which are a little more powerful than Boolean variables. For example, in this case, in the first case, we will use goes X, Y to indicate X goes to Y. So here a variable is X, this is a variable. X and Y are both variables. X and Y are both variables, and this go is what is called a predicate symbol. It's called a predicate symbol. A predicate symbol is just like a Boolean variable. A Boolean variable is a predicate symbol with no arguments. A Boolean proposition or a Boolean variable, if I had written B, it can take true or false. Similarly, a predicate can also take true or false, but it can have some variables as arguments. So these variables as arguments become a very important aspect in which we enhance the power of propositional logic to get this new logic. In addition, we talked about two things. One was we needed to model some and we needed to model all. To model some, we use this symbol which we write as a reverse E, and it is called the there exists symbol. There exists is equivalent to some. The other we model as a V which is cut like this, and it is called the for all symbol. So the there exists symbol and the for all symbol are two symbols that we add to our original connectors of and, or, not, and implies. So now we have added variables. We will later see how we add constants and constant functions. We will also add what are called function symbols, but we will do that later. We are added predicate symbols as we saw here, and we added these two new connectors. Let us go to the second example. In the second example, we will add several new predicates. For example, contracted, dependable, engineer. So we will add new predicates like contractor X, which means X is a contractor, dependable X, which means X is dependable, engineer X, which means X is an engineer. Similarly, we will do it for others, and then we will see how we codify them into sentences. Let us now do some examples. So this logic that we have talked about is also called predicate logic, or it is also called first order logic. Boolean logic or propositional logic is also called zeroth order logic because it has got no concept of variables. So now let us go and start working out the example in a formal manner using predicate logic. So let us go to this example. Wherever Mary goes, so does the lamb. Mary goes to school, so we go to example 1 below. Wherever Mary goes, so does the lamb. Mary goes to school, so the lamb goes to school. As we said before, we use a new predicate x goes xy, where x and y are variables to represent x goes to y. And we use these two new connectors, there exists and for all. And how do we model the first sentence F1? Our steps are the same. We model and codify the sentences. So we write for all x goes Mary x, where Mary is a constant symbol, implies goes lamb x, where lamb is a constant symbol, and this x is the common variable between Mary going to a particular place and lamb going to a particular place. So we say that whenever goes Mary x is true, goes lamb x is true for every x. This is the meaning of wherever Mary goes, so does the lamb. So this is how we codify this sentence. The second sentence is a straightforward sentence. It did not contain any variables. It says Mary goes to school. So we have got two constants. Mary, so we have got actually three constants here. The constants are Mary, lamb, and school. So the constants that we use are Mary, lamb, and school. These are the three constants that we use in our formula. And goes lamb school is the second goal. So given wherever Mary goes, so does the lamb, F1. Mary goes to school, F2. So, or therefore, the lamb goes to school, F3. And we use our same mechanism of saying that we now must prove F1 and F2 implies G, this formula. Now this is a formula in predicate logic, and we must prove that this formula is a tautology, or this formula is valid. That means that this formula is always true. So this is how we use predicate logic to code this one. Let us go to the second one, which is our example 2. In our example 2, we have no contractors are dependable. Some engineers are contractors. Therefore, some engineers are not dependable. So as we have discussed a little earlier, we use 3 predicates: contractor X to define that X is a contractor, dependable X to define X is dependable, engineer X to define X is an engineer. Using these variables, these predicates, whereas goes XY had got 2 arguments, here these predicates have got only 1 argument. Predicates can have as many number of finite arguments. Now let us see how we model the first one. No contractor is dependable. So we could model it this way, saying that contractor X implies not dependable X. That means for all X, if X is a contractor, then X is not dependable. This is how we could write no contractors are dependable. There is an alternative way. We could write it in the negate way. That means a contractor and dependable. In the existence of a person who is a contractor and is also dependable is not possible. So we say that there exists X, contractor X and dependable X is not true. That is how we have written this formula. If we just reverse back to see what is the formula we have written, there exists X, contractor X and dependable X. This thing is not true. This is a not symbol here. These two are equivalent, and we shall see how De Morgan's laws also hold in such things. Let us look at the second one. Some engineers are contractors, which means that there is a person who is an engineer and a contractor, which is true. Somebody could have asked me that why didn't I write there exists X, engineer X implies contractor X. Why I did not write this is because this formula could be true if there was no engineer. If nobody was an engineer, this formula would still be true. But I have said that some engineers are contractors, which means that I am expecting that there is some engineer who is a contractor. So, if there exists an engineer, then the truth of this formula will be the truth of this formula as same. So, if we write this and there exists X, engineer X, then this formula is the same as this formula. That is why we don't write it as an implies, but we write it as an and. What is the third sentence? Therefore, some engineers are not dependable, which means that there exists an engineer who is not dependable. Normally, we see how this is codified, and these are the 3 formula. The first sentence is modeled as for all X, contractor X implies not dependable X, or this is the alternative. The second formula is modeled as there exists X, engineer X and contractor X. The third, or the goal, is modeled as there exists X, engineer X and not dependable X. And all we have to prove again as follows: F1 and F2 implies G is valid. That means it is always true. We come to example 3. Example 3 has got 4 sentences. All dancers are graceful. Ayesha is a student. Ayesha is a dancer. Therefore, some student is graceful. So, how do we model it? First is identification of predicates. So, what predicates do we identify? Graceful X. The second is student X. And the third is dancer X. Graceful X means that X is graceful. Student X means X is a student. Dancer X means that X is a dancer. And we have one constant symbol, which is Aisha. We will use the mechanism of writing constants by starting with capital letters and predicates starting with small letters and variables starting with lowercase letters as well. That is the convention we will use. What is our formulae now? F1. Our formulae is all dancers are graceful, which means for all X, dancer X implies graceful X. The question is, why didn't we write for all X, dancer X and graceful X? Now, this formula, what is the difference between this one and this one? In this one it says if somebody is a dancer, then that person is graceful. And this person says everybody is a dancer and graceful. Therefore, if a person is not a dancer, then this formula will become false. On the other hand, if somebody is not a dancer, here this formula will become true. Therefore, this is an incorrect formula. The second sentence, F2, Ayesha is a student. So we write student Ayesha. F3, we write Ayesha is a dancer. So we write dancer Ayesha. Therefore, some student is graceful. So how do we write this? There exists a X such that X is a student and X is graceful. So we have now modeled the first sentence as for all X, dancer X implies graceful X. The second sentence as student Ayesha. The third sentence as dancer Ayesha. And the goal which we want to derive from the first three sentences as there exists X, student X and graceful X. And what do we want to prove? Again as follows, F1 and F2 and F3. This is what we want to deduce, is G. This is our deduction, and we want to prove that this is a tautology. We come to our fourth example. Our fourth example says every passenger is either in first class or second class. Each passenger is in second class if and only if the passenger is not wealthy. Some passengers are wealthy. Not all passengers are wealthy. Therefore, some passengers are in the second class. We know that this is derivable. So how do we formally go through the codification process? So what are the predicates? Px is passenger X. Fx is first class X. Sx is second class X. Wx is wealthy X. So we are using these first class, second class, wealthy. So each passenger X, this is passenger. This is X is in the first class. This means X is in the second class. And this means X is wealthy. So once we have got our four predicates, each of them is a single argument predicate. There are no constants here. How do we code our first sentence? Our first sentence is very interesting because it talks of either. Now there are two ways of doing either. So it talks of either and or. There are two ways of doing it. One is we could use what is called an inclusive or. The other we could use what is called an exclusive or. If we use an inclusive or, then we will write passenger X implies first class or second class. For all X, passenger X is in the first class or in the second class. Wait, I need to do a little erasing. And if we use exclusive or, that means if we write it as F1 dashed, then we have to write Px, because both of them being in the first class as well as in the second class is not true. So it will either be one of the following. It will either be Fx and not Sx, or it will be not Fx and Sx. So it will either be in the first class or in the second class, but not both. So depending on the problem at hand, you will do this codification. In this case, we would be easy following this step, but this is also a possible encoding. How do we do the second one? The second one is a little tricky again because it talks of if and only if. It says each passenger is in second class if and only if it is not wealthy. She is not wealthy. So if the passenger is not wealthy, then is in the second class, and if the passenger is in the second class, then the passenger is not wealthy. So again we write for all X, passenger X implies. Now there are two things that we have to do. What we have to do is that both of them are true. So there are two parts to it. If the passenger is in the second class, it implies that the passenger is not wealthy. And if the passenger is not wealthy, then again the passenger is in the second class. So there are these if and only if is to be modeled by this sort of a mechanism. So this gives us F2. So this is F1, this is F1 dashed, this is F2. Some passengers are wealthy. So F3 tells me that there exists X where passenger X is true and wealthy X is also true, which means that some passenger is wealthy. What is our fourth statement? Not all passengers are wealthy. So how do we write all passengers are wealthy? We can write for all X, passenger X implies wealthy X. And what we want to say is that this statement is not true. We could also write this in a slightly different way, which means F4 could also be that there exists some passenger who is not wealthy, which means some passengers are not wealthy, means that we could write that there exists X, passenger X, and not wealthy X. And we will see that both of these are equivalent. And how do we write F5, or which is our goal? Therefore, some passengers are in the second class, which means that there exists a passenger and that passenger is in the second class. So now we have codified for our whole case, we have codified F1, which is every passenger is either in the first class or in the second class, which has got two options. We have codified F2, which talks of if and only if. We have codified F3, which says some passengers are wealthy. We have codified F4, which talks of not all passengers are wealthy, and we have seen two equivalent versions of them. We have codified the goal, saying that therefore some passenger is in the second class. And finally, our deduction will be F1 and F2 and F3 and F4 implies G. This is always true. So this is how we model this example, the example 4. So today what we have shown is that we have discussed what is called predicate logic and how it moves from propositional logic. In propositional, so we have actually shown how we move from propositional to predicate logic. And here we introduce the concept of variables. We introduce the concept of constant symbols. We introduce the unique concept of predicates, which is the extension of Boolean variables. We introduce two connectors, for all and there exist. And then we follow the same steps of codification of formula, of sentences into formulae, and then development of the combined formula. For which we want to prove that the formula is valid or satisfiable or whatever, etc. So having got this movement from propositional logic to Boolean logic, we will now in the next class examine predicate logic in more details and see what are the intricacies of predicate logic. We will see how we can model problems, how these interact with each other, and what do we mean by a validity or a satisfiability, and we will discuss the power of predicate logic.